Okay, we are on chapter 12. We'll go 12. 12 sounds like a winner. So last time, again, we sort of went over alcohols again. And again, as we talked about, alcohols has that functional group of the OH. We talked about also classifying alcohols as primary, secondary, or tertiary. Again, that is kind of similar how we do with our carbons. It is the carbon that has the OH attached to it, and then how many carbons are directly attached to that carbon gives you your primary, secondary, and tertiary alcohol. We also talked about reactions involving primary alcohols. Again, if you oxidize it, you do get an aldehyde, which has the functional group of carbon, oxygen, double bond, and a hydrogen. And as we'll talk about as well, and I think we did a little bit as well, if you further oxidate it, you could get a carboxylic acid, which is another organic group that has a carbon, oxygen, double bond, and an OH. If you have your secondary alcohol, you can oxidize it to a ketone. Ketone being a 3-carbon run, where in the middle carbon you have the carbon oxygen double bond. Will not oxidize anymore at that point, so no oxidation at that point. By the way, the carbon oxygen double bond is what is sometimes referred to as the carbonyl carbon, our group. We also talked about some other organic guys. We talked about thiols, which have basically similar type of group to our alcohols, has an SH as the functional group. We also talked about a reaction that thiols do, which makes a disulfide bond or bridge. And really that's a result basically of 2 thiols. And again, I'll just use R for the rest of the carbon chain there. Basically here we're going to lose the H's, and that will put together our thiols with this disulfide bond here, our bridge. And that's really an oxidation, which is the loss of H2. You could do the opposite reaction that we talked about as well, which is the reduction, where you basically add the H2 back in, breaks them back apart. We also, I think, finished up as well talking about ethers. So ethers have a functional group of a carbon, oxygen, carbon. So ethers has a functional group of carbon, oxygen, carbon. Here, oxygen really inserted in between the 2 carbons. So you always will have this sort of run here as a functional group for an ether. We talked about naming ethers, and really we went with the common naming of ethers, not really the IUPAC way of naming. And really to do that, you basically just kind of go left and right of the oxygen, and you basically name the groups in alphabetical order. So again, if you just sort of think of the oxygen as your centerpiece there, to the right is an ethyl group, to the left there is a methyl group. And again, putting this together in alphabetical order gets you ethyl, if I spell it right there, ethyl, methyl, and just put ether at the end. Again, I might have mentioned the proper IUPAC way of naming, which I don't think your book does, and we'll go with the common, but you basically name this guy and put OXY at the end of it. So this is what is known as methoxy for the methyl group. The longest carbon chain is basically 2 carbons versus ethane, and this is also known as methoxy ethane. But again, we will go with the more common name way of naming it as well. Any questions on any of that stuff there? We talked about, I think, the last time. Yeah. There? Yeah. Any questions on any of that stuff there? Yeah. So we're going to finish up here, talk a little bit more about alcohols, and we're going to kind of review some of those reactions. We kind of did them a little bit earlier than in the slides there, but we'll kind of go over them again. And then we're going to get into some more carbon oxygen containing groups, which are aldehydes and ketones, which should be good for this week, I think, for your lab, if I'm not mistaken. So that should be good. Good. Yes. Okay. Okay. So I don't recall if we talked about solubility or not. I think we did, but let's just talk a little bit about the solubility of alcohols and ethers in water. So in terms of alcohols, because they do contain that OH group, they can definitely participate in hydrogen bonding. And that really gives them a couple of sort of characteristics. First off, they are fairly soluble in water, up to about 6 carbons or so, or less, 6 carbons or less. And again, because when water's there, they can perform the hydrogen bonding between the negative side, say, of water and the positive side of our alcohol, making our hydrogen bonding. Now, once you build out about 6 or more carbons, as we might have talked about as well, you're just kind of increasing the nonpolar part of this molecule. And it has just a small polar part. So sometimes, again, it's sometimes referred to as steric hindrance. It basically just means things get in the way. So you got this really big kind of non-polar part. It makes it really hard for water to get in there and sort of interact with the OH group that's on the alcohol. So the solubility really does drop a lot. In addition, as you can see there, that's like really 5 carbons here. It becomes almost insoluble at 5 carbons. But it just kind of gets in the way. Also, in addition, if you have more OH groups on alcohols, for example, obviously that would increase the solubility. Again, more OH groups would allow it more places to interact well with water. Also, alcohols in general have very high boiling points and melting points. And that is because of its ability to hydrogen bond with itself. So if you remember, hydrogen bonding is a relatively strong intermolecular force. So because it's held together really strongly, it takes a lot more energy to break them apart at, say, the boiling point to get it into the gas phase. Also takes a lot more energy to sort of break it apart into the liquid phase. And because of that, that translates to much higher boiling points and melting points than something we see like alkanes or alkenes. Thank you. Or alkynes. All these guys basically are just carbons and hydrogens, which basically will be used in dispersion forces. And these dispersion forces are those relatively really weak type forces that hold everybody together. So because they're held together by these really weak forces, things like alkanes, alkenes, and alkynes, they have very low melting points and boiling points as opposed to, our alcohols. That's also why our alkanes and stuff like that, several of the first ones are very much gases because they're held together by these weak dispersion forces. Now, ethers, on the other hand, which do have this oxygen in the middle, and this is a polar bond between carbon and oxygen, with this guy being a little bit more negative. Ethers cannot hydrogen bond with themselves because they lack the hydrogen to do so. But, it can participate a little bit with water as well and do some hydrogen bonding to water rather than itself. So it does have some solubility. Again, kind of the same idea. You're going to lose a lot of that solubility with the more carbons you sort of build out on it. But there is some. With ethers, they definitely would have much lower melting points and boiling points than alcohols, again, because of its lack of ability to hydrogen bond as well. Any questions on any of that there? That's a negative? Yeah. So remember, right, if there's sort of a polar bond, there's separation of charge because of the unequal sharing of electrons, creates sort of a partially positive charge on one side and partially negative charge on the other side. Other questions? Okay. Phenols, let's talk a little bit about the solubility of phenols. They are slightly soluble in water. They have that OH group, which means they can hydrogen bond with water. But they do sort of do almost like an acid-base type reaction where this acts as an acid, this sort of acts as a base, and that H plus, kind of like Bronsted-Lowry, sort of goes over there, and as you can see, makes like H3O plus, and then we make this sort of ion here, which comes off when the H plus comes off. So they're slightly soluble because of that. They are not really greatly soluble like you see with regular low carbon alcohols, and that's because it's got this big carbon hydrogen ring basically attached to it. That's that benzene ring we talked about that has the sort of 3 double bonds in there. So, you know, you got this kind of biggish sort of ring that's pretty much non-polar. So it does sort of decrease the solubility that you would expect to see there as compared to regular low carbon sort of alcohols. Any questions on alcohols, solubility? So we talked about naming them, obviously. You need to be able to classify them, name them. You need to know the reactions that occur. And any questions on any of that there? Okay. All right, so indicate whether each of these would be soluble in water and explain why. Take a second. Looking at these, they are both basically obviously alcohols here since they have these groups. Now, when we look at the first one, we got about 6 carbons or so. And as we saw from that table, really about 5 carbons, it becomes pretty much insoluble here. So because of this big sort of non-polar part of this alcohol here, we would expect, you know, there's only the small polar part, we would expect it to probably be insoluble in water. Again, just that big carbon part gets in the way, as I mentioned earlier, for this guy to interact. As opposed to here where we have ethanol. And again, we have a much smaller non-polar part of this alcohol. It's not going to get in the way. It's going to allow, you know, water and everybody to get over there to this OH group. And it's going to allow it to do its hydrogen bonding there with water and interact with water. So we would predict that our ethanol here would be soluble in water. So again, based on that table, about 5-ish is pretty much where you run out of solubility if you got 5 or more carbons. But anything less than that should be relatively soluble. And again, it starts to decrease with the increasing number of carbons that we see. Yeah, so yeah, on that table, they went with 5. So about 5 or less carbons is going to be actually less than 5, I guess is a better way to say that. Less than 5 carbons. It's going to be probably some type of soluble in water. But you get about 5 or more carbons on an alcohol, you're pretty much going to become insoluble. Again, it just builds out of too much of a non-polar part for it to be able to interact well with water. Other questions on that? All right. So the next type of organic compounds we're going to talk about are aldehydes and ketones. So these are also oxygen-containing compounds. Aldehydes have the functional group of a carbon-oxygen double bond and an OH. Oftentimes, sometimes written in formulas as COOH is sort of how it's written. Ketones, on the other hand, as I mentioned a second ago, have always a 3 carbon run at minimum. And in that center guy, you have that carbon oxygen double bond happening. The simplest ketone known as acetone or propanone, and that's sometimes referred to also as dimethyl ketone. It's colorless. It is, you know, like nail polish sort of remover and stuff like that. Now, I'm sorry, I wrote the wrong form. My bad there. I wrote a carboxylic acid there. That would definitely not be right. Sorry about that. Had that in my head. Let me fix that. That is what it should look like right there with the H. There you go. So it should look like this, carbon oxygen double bond with the H on the aldehyde. Again, the ketone, 3 carbons in a row there. What I wrote is a carboxylic acid, which is one more step down the road. Now, because of the aldehyde having that H there at the end, it is always going to be at the very end of the molecule where you find that functional group. So the aldehyde will either be on one end or the other end, the functional group for it. By the same token, because for a ketone you need really a 3 carbon run, you'll never find that carbon oxygen double bond at the end. It's got to be in from the end at some point. It can never sort of be at the end of the carbon oxygen double bond, while this guy always has to be at the end because of that hydrogen that is there. So our carbonyl group that's attached is this carbon oxygen double bond, and it is a polar bond between this guy is carbon, this guy is oxygen. Oxygen being more electronegative, more partially negative on it, more partially positive there on the carbon. This also gives these guys some ability to interact with water and hydrogen bond through that polar spot. It cannot really hydrogen bond again with itself, but it can sort of participate a little bit with water there through the C carbon oxygen double bond that occurs. Again, that carbon oxygen double bond is what is referred to as the carbonyl group. That is that guy right there. Yes. So again, when they say perhaps sometimes the carbonyl carbon, that is the carbon they're talking about, the one that has the double bonded oxygen to it. So this guy would be sometimes referred to as the carbonyl carbon. And again, both of these guys have that group in it. So this carbonyl group in our aldehyde has a hydrogen attached, and obviously, like I said, a 3 run of carbons there in our ketone. Here's a couple of examples, aldehyde on the bottom there, and our ketone. So here's our ketone, has 1 carbon, 2 carbons, 3 carbon run with the oxygen double bond there in the middle. And that's different than our aldehyde, which is at the end here, carbon oxygen double bond, and a hydrogen is part of it there. The way we go about naming these guys are a little bit different for each of these, but not too bad. They are also going to be based off of obviously the first 10 alkanes, as we've been talking about with all these other organic groups. The goal here is obviously going to count the longest carbon that obviously has the carbon oxygen double bond part of the longest carbon chain that you're looking for. So when we look at these guys, an aldehyde may be written CHO, and that would be our aldehyde group, which again is the same as a carbon oxygen double bond and an H. And our keto group sometimes written like that. In line structure, that is sort of what it looks like for our aldehyde. You just kind of draw in your double bond on the carbon you need, and you do write the hydrogen there at the end. So it doesn't imply that it is a carbon at the end there. So you need to put the hydrogen. And a ketone is pretty much just wherever you need that double bond, you just lay up a double bond. And again, that is sort of what a ketone looks like in sort of line structure. And this is once again 1 carbon, 2 carbons, and 3 carbons in a row that has a double bond in the middle there in terms of what they look like. Obviously, to the left there is condensed formula here. And in each of these there, I would say probably most of the time when people write sort of condensed formula, they do sort of draw out the functional group for these guys. You know, I would say maybe in a textbook you might see something like that, but usually for us and stuff like that, we usually will draw out the sort of functional part of it when you're doing a condensed structure rather than just kind of write CO or CHO in there. So let's talk about naming aldehydes. Aldehydes are named off of the first 10 alkanes, and pretty much you just lay up an AL at the end of it. So if you have this guy, which is basically your simplest aldehyde you could get, that is one carbon, which is based off of methane. We're going to drop the E, and this would be known as methanol, AL, not OL, because that would be an alcohol. So this would be AL here. And again, you can go left or right on this guy, but that is your functional group right there. Do you have two carbons? Once again, two carbons is based off of ethane with our aldehyde group right there. Okay, we drop that guy and it becomes ethanol, AL. Obviously, three carbons would be propanol and butanol. There are some common names that sometimes you'll see here, and probably the one you should know maybe is formaldehyde, is basically this guy right here. Methanol is formaldehyde. They use that right sometimes, and preservative there in biology sometimes smells wonderful. You get your methanol going there, which is also formaldehyde. We probably won't use these. Again, are common names for 2, 3, and 4 carbons that are aldehydes. We probably won't use too much of those names. We'll use the more IUPAC name. So for example, 3 carbons there. Once again, our aldehyde group, and based off of propane would be propanol, AL. Now, a couple of things about sort of the functional group. So like what we did with alcohols, where we had to perhaps give the location of where the OH group is, and we have to do that, with double bonds and triple bonds. You do not need to do that here with aldehydes, and that is because the aldehyde group will be at one end or the other. It's always got to be at the end. And because it is the functional group, it does take the priority in terms of numbering. So if there were other groups attached, although you don't need to include it in the name, this will always be carbon number 1 where that group is. So that carbonyl carbon will always be carbon number 1 in terms of numbering for other groups that may be attached. Same thing here. This guy would have been carbon number 1 in that particular case. But again, you don't need to give sort of location of that because it could only be at the end. So it's assumed to be there. And again, it's assumed to be carbon number 1. But you still do give the carbonyl carbon there the priority in terms of numbering in case you do have other groups sort of attached. Question on that there. So here's our first 4 here: methanol, ethanol, propanol, and butanol. And again, these are the sort of the line structures there where our carbons do come in. So, if we had something like so if we had something like this, we would look at the longest carbon chain that obviously contains the aldehyde group in this case. And in this case, it is just straight across here. We'll do that for us. Obviously, that has the aldehyde group there. Once again, that is going to be 1, 2, 3, 4 carbons, which would be based off of butane, and this would be butanol, AL. Once again, we don't need to give the location of this group, but it is going to be carbon number 1, and that's going to be important because then that would make that carbon 2, and that would make that carbon 3 where we have our chlorine attached. So this would be 3-chloral butanol. So again, we use that carbon oxygen double bond as carbon number 1 for our purposes of numbering, but you do not have to incorporate it into the sort of aldehyde part of the name. Any questions on that there? Yes, sir. Yeah. How would you know it should be butanol? Is that what you're asking? Yeah. So it's based on the longest carbon chain that has the carbon oxygen double bond in it. So this is 1 carbon, 2 carbons, 3 carbons, 4 carbons. And that's the longest carbon chain that still contains the functional group that's there. So that's based off of butane. And because the functional group is an aldehyde, we basically drop the E and put Al at the end of it. And that tells you that it is an aldehyde that has basically 4 carbons. So it's just like everything else. You want to always go for the longest continuous carbon chain. But again, kind of like with the OH group or the double bonds, it has to contain obviously the functional group here as part of that longest carbon chain. And then that's how you base your name on it. And then again, wherever that carbon oxygen double bond is located, that carbon will always be carbon number 1 in terms of numbering. Other questions? Yep. All right, so why don't you give this one a go here, see what you come up with. And let me draw a few more here. Okay, let's take a look. So we'll start with the one that was originally there. And if we do our longest carbon chain, that looks like it is straight across there. And that has 1, 2, 3, 4, 5 carbons. Now, could you have started here, went up and went to the left? The answer is no, because that did not include the functional group here. So you wouldn't want to go that way. It then has to have the functional group in it. So this is really the only way you could go to get it. Your other option would have been actually to go this way to the right, would have gave you the functional group, but obviously only gives you 3 carbons, which is much smaller. So that's not the way you want to go either in that particular case. All right, so we got 1, 2, 3, 4, 5 carbons. This is our aldehyde group right there. So 5 carbons is based off of pentane. It does become pentanol. Once again, we do not have to give the location where that carbon oxygen double bond, but for the purposes of numbering, it is going to be carbon number 1 here, which means this would be carbon 2, that would be carbon 3, that would be carbon 4, and that would be carbon 5. And that means that carbon number 2, we do have a methyl group there, and that would get us something like 2-methyl pentanol. Any questions on that name there? All right, so my big scribble over here that kind of went over. Also, if we go straight across on this one, is going to give us really our longest carbon chain. Once again, you can start with the guy at the bottom, and really your only other option would be to go left, which would only give you 3 carbons, and obviously not as much. So I got 1, 2, 3, 4, 5, 6 carbons that are there. So 6 carbons are based off of hexane. Again, we see our aldehyde group here at the end. And that would then be hexanol, Al. Again, not OL, otherwise that becomes an alcohol. In this case, my aldehyde group is on the left-hand side there, which means for the purposes of numbering, that would be carbon 1. That would be carbon 2, 3, 4, 5, and 6. And once again here, actually at carbon number 2 is where we see our methyl group. So that would be 2-methyl hexanol. Any questions on either of those names there? All right, so now we're going to draw some, and like normal, we always want to kind of start with the name and kind of work our way to the left there. So first off, I see heptanol. Al tells me it's an aldehyde group. The heptane part tells me it's 7 carbons. This is where I regret that choice. 1, 2, 3, 4, 5. I lost track there. I'm going to go with 1, 2, 3, 4, 5, 6, and 7. Now, this is a aldehyde group. Again, we know that because of the Al. Once again, because you're drawing, you could put it on either side there. I'm going to put it on the right-hand side, which means on that last carbon, I want to put my actual functional group in there, which is the carbon-oxygen double bond with the H. Obviously, if you put it on the other side, it looks the same, just with it on the other side. That really takes care of this part of it. Because I chose to do that and put my group over there on the right-hand side, that means for sure, for me, That is carbon number 1, which means right next door would be carbon number 2, where I should have a chlorine attached. And also at carbon number 4, I should have a chlorine. And again, for me, it would be here, would be carbon number 4. That is what the dichloral means. And just like everything else we draw, we're just going to fill it up there with hydrogens to get carbon to 4. So the guy right here just needs 1 hydrogen. Guy here needs 2. 1 here, 2, 2, and 3. Again, if you put the group on their side, yours should just like that, but flipped around, basically. Any questions on that drawing there? All right, and lastly here, we'll go this way again. So we see pentanol. Again, the Al tells me it's an aldehyde. The pentane tells me it's 5 carbons. So 1, 2, 3, 4, and 5. I am once again going to put my aldehyde group on the carbon on the right, but once again, you can put it on the other side if you want. That takes care of that. Because I did that, once again, that will be carbon number 1 for me, which means carbon number 3 would be down the road here. And that will put my methyl group. And again, we're just going to fill in our hydrogens. So we need a couple there. This guy has 3 lines, so he needs 1. This guy has 2 lines, it needs 2. And this guy has 1 line, it needs 3 in that particular case here. Any questions on aldehydes, how to draw them, how to name them? The good news is that group's always at the end, so that's a good place to, it's like I should put it there. Okay, then let us talk about how we name ketones, which is our other group here that we're talking about that has that carbonyl group. Again, as I mentioned before, unlike aldehydes here, ketones will never have that carbon-oxygen double bond at the end. It will always got to be at least 1 in and can be more in from the end, but it will never be at the very end because of the need for always a 3 carbons in a row with a double bond in the center of those 3 carbons. So again, we'll never find itself there at the end. So the IUPAC way of naming ketones is we basically put ONE at the end of it. So because you need 3 carbons in a row, the smallest ketone you could have must have 3 carbons. So that is like 1, 2, and 3, again with the double bond in the middle. Filling in our hydrogens here. That is basically your simplest guy you could have. This is 1, 2, 3, which is based off of propane. Dropping the E and putting basically 1 at the end of it becomes what is known as propanone, O-N-E, at the end. And that is your simplest ketone you could have. You can't have anything with 1 or 2 because you need 3 carbons, basically. So that's the smallest you could go. Now, unlike aldehydes, because that OH group or a carbon-oxygen double bond group, I'm sorry, the carbon-oxygen double bond group is definitely interior. There can be times where it can be at multiple locations on the carbon chain. So right around 4-ish or so carbons, you do need to give the location of where that carbon-oxygen double bond is located. So much like with the OH group, double bonds, triple bonds, truthfully, like 5 or more carbons is really where it's at. But around 4 or 5 carbons, you should give sort of the location of where that carbon-oxygen double bond is. Really, so it looks like your book doesn't do it, but sometimes you'll see people put a number for this guy, but it really shouldn't, because it could only really go at this carbon, which would be carbon number 2, or that carbon, which would be carbon number 2 as well, no matter which way you kind of go. And that is what is known as butanone. Here, though, when we get 1, 2, 3, 4, and 5, this is what is known as 3-pentanone. The 3 is the location of where that carbon-oxygen double bond is located. So about 5 or more carbons, you do need to give the location of it. The common way of naming it is kind of like what we did with ethers. You kind of think of the carbon-oxygen double bond as the center. To the right and left are two groups. They are both methyl groups. So this would be known as dimethyl ketone, would be the common name. But for us, we will go with the IUPAC way of naming. Yeah. But you will sometimes still see the common name used a lot with ketones. But for us, you should do the IUPAC way of naming. Also works on a ring type structure. So if we look at this guy here, it's down that one. This is a 6-member ring, which is cyclohexane. This is actually the ketone group right there on top. So in case you can't see it, this is 1 carbon, that is 2 carbons, and that is 3 carbons. So that is a 3-carbon run right there with the double bond in the middle. And that would make it go from cyclohexane to cyclohexanone, O-N-E at the end. And much like this ring structure, you don't need to give the location of where that double bond is because it's assumed to be carbon number 1, but it's important for numbering other groups. So this would be carbon number 1, which means to get to my methyl group here with the smallest number, I need to go clockwise to do that. If I went counterclockwise, I would have a bigger number. So I want to go clockwise here, which would be 2 and 3. And that is how we get to 3-methyl cyclohexanone. Any questions on that there? So ketones, you do need to give the number about 5 or more carbons involved. Again, you want to do it to give that guy the smallest number. So whichever way gives the carbon oxygen the smallest number. And then obviously once you sort of lock in which way you're numbering, everybody else gets numbered accordingly. All right, so why don't you try this one? We'll draw a couple more here, see what we end up with. Okay, let's take a look, see how you're doing. So we'll start with the one that was originally there. And I'm just gonna go straight across here as that does have my ketone group. And that is 1, 2, 3, 4, 5. You also, if you wanted to, could have went up and over as well. Again, you would have to go towards the group there, and it would also give you 5, 1, 2, 3, 4, 5. So much like anything, you could choose either way. As we talked about, maybe the straightest way might be the best. That also gives us obviously a group right here, which is a methyl group. So we had, we got there 3, 4, 5. So we see the ketone group, our 3-carbon run right there at towards the end of it. So there's our ketone group right there happening. So with that, we could get our name. This is going to be Pentanone, O-N-E. Because it's 5 or more carbons, we do need to give the location of the carbon-oxygen double bond. And once again, we want to give it the smallest number. So it's going to take the priority. So you can just look at it and hopefully see you should go right to left here in terms of numbering. Would do that for you. That means that our carbon-oxygen double bonds at carbon number 2, so that becomes 2-pentanone. Because we locked in that numbering, that puts our methyl group over there at 4, and that gives us 4-methyl 2-pentanone. Any questions on that name there? All right, looking at the guy to the left there, this whole thing looks like the biggest carbon chain. That is a ring that has 5 carbons in it with our ketone group. And once again, this is our ketone group right here, 1 carbon to 2 carbons to 3 carbons with the double bond hanging off the end there. And that is going to get us a cyclopentane, which then becomes cyclopentanone. Again, here, you do not need to give the location of the carbon-oxygen double bond because it is a ring, but it is assumed to be carbon number 1, as we talked about. In this case, if we go clockwise, 2, 3, 4 to our chlorine. If we go counterclockwise, 1, 2, and 3. So in this case, we probably would want to roll here counterclockwise to get there. That puts our chlorine at 3, and that would be 3-chloral cyclopentanone. Any questions on either of those names there? All right, then we're going to draw some here. So once again, starting backwards. ONE tells me it is a ketone, and hexane basically tells me it's 6. So that seems like a good place to start. So that is 1, 2, 3, 4, 5, and 6. Once again, you can put the ketone group on the left-hand side or the right-hand side. So I will mix it up and go left-hand side. It needs to go second carbon in on my 3-carbon run. So starting at the left there, 1, 2, 3. Second one in where my double bond would be. And that is because it is 2-hexanone, right? So that is where it needs to be in this particular case. Any questions on that there? So that takes care of the 2-hexanone part. Because this is carbon 1 and that is carbon 2, that means carbon 3 would be right next door where I would put my chlorine. And at this point, everything else is going to be hydrogens. So guy at the far right needs 3 to get to 4 bonds. The guy next to it needs 2. Guy next to it needs 2. Guy next to it just needs 1. And the guy next to that needs none. The guy at the end needs 3. Yeah. Any questions on that one there? All right. Now, lastly here, we got heptanone. So what I'm going to do is actually erase, I think, this name here. Give me somewhere to scribble. All right, so we'll draw it there. Okay, so obviously ONE tells us it's a ketone, and heptane tells me 7. Should be smaller. 1, 2, 3, 4, 5, 6, and 7. In this case, it is at carbon number 3. So again, I need to go 3 carbons in on the left or the right. Again, your choice. I'm going to go left, which means I'm going to do that, which means really here carbon 2, 3, and 4 is my 3-carbon run there with the double bond happening at carbon number 3, which is obviously being carbon number 1. Because that's carbon number 1, carbon number 2, carbon number 3, that means at carbon number 4, which should be right next door, I have a dimethyl situation happening, which looks like this. Now I have a hydrogen situation happening to get me to 4. So that guy needs 3. That guy needs 2. That one needs 2. This one needs none. The one next to it needs none. This guy needs 2. And that guy needs 3 in this case. A question on the ketones here, how to draw our name. Yeah. What are we talking about? On the very top structure, is that what you're talking about?
Oh, okay, never mind. You're counting the
Okay.
carbons.
Yeah. So I erased the name, but the guy on the top was 1, 2, 3, 4, 5, 6. So that was hexanone. So that's why there's 6 carbons. And yeah, okay. This is not an H. That's for number 2. Yeah, counting the carbons. Yeah. Other questions? Okay. So let's talk a little bit about aldehydes and ketones in water and sort of their solubility. They can't form hydrogen bond with water between the carbonyl groups. So as I mentioned before, they cannot hydrogen bond with themselves because they do lack the hydrogen. But because they have that polar carbonyl group where this guy's more negative, this guy's more positive, when you got water floating around, it is negative and positive. It's able to do some hydrogen bonding there with water. That is going to make them very soluble, but again, limited based on carbons. So about 4 or less carbons, you're going to have some good solubility of your aldehydes and ketones. But again, as you build out, like everything else in sort of organic, as you build out more and more carbons, it just gets harder and harder for the water to sort of get in there to interact with that group, and the solubility pretty much goes away. So aldehydes and ketones will be pretty much soluble for less carbons. They also or boiling point and melting point than alcohols, again, because they cannot hydrogen bond with themselves like alcohols can. They will have a lower boiling point and melt than alkanes, but they will not have a higher one than alcohol. So alcohols at this point is still our champ in terms of boiling points and melting points. So as you can see here, these are our aldehydes, pretty soluble there, less than 4. And again, these are our ketones here. You know, you start losing solubility as you build up those carbons on there. And as we talked about, really does sort of get in the way of everything. So some important aldehydes and ketones, acetone, which is propanone, is a solvent used in nail polish remover. You know, when you open that in a car, it smells great. No, it is acetone. Formaldehyde, as we talked about, which is methanol, used again to preserve things like in biology. Not sure what they got in there. It looks like almost like a squid. Some other important aldehydes and ketones. This is benzaldehyde. It is our nice almond situation. And here is our aldehyde group. This is vanilla. Again, once again, our aldehyde. And this is our ketone, which is our ketone group there. I feel like there should be an H perhaps there to make it an aldehyde. All right, so let's classify each of these as aldehydes and ketones. So A would be it is a ketone. Again, we got our 3 carbons in a row with the carbon-oxygen double bond. So again, that is a ketone. And by the way, that is 1, 2, 3 carbons, 4 carbons. That is butanone, right? Guy over here would be a aldehyde. Again, that is the functional group right there. That is a 2-carbon aldehyde, which is known as ethanol, Al at the end of it. This guy C would be a aldehyde as well. Once again, there's our functional group. That is right there, carbon number 1, 2, butanol. That's right underneath. And lastly, this guy here would be a ketone. That is 1 carbon, 2 carbons, 3 carbons in a row with the double bond. So that would be a ketone. That is based off of cyclohexane. And again, that would then become cyclohexanone, N-O-E-O-N-E. Any questions on those classifications? Okay. Put my finger down there. So again, our aldehydes, ketones are going to be soluble in water. Again, less than 4 carbons. And again, they will have some boiling points less than alcohols, but definitely more than your alkanes in terms of those guys. Good. Yes. Take a look. So we will see our ketone group, just in case they weren't nice enough to tell you. That is our ketone group there in the first one, our 3 carbons in a row. And our double bond off of that 2nd carbon there. So we know both of these are ketones, which means they should end up with an ONE at the end of it. We're going to just do the longest carbon chain, which in this case is the whole thing. And that's going to be 1, 2, 3, 4, 5, 6 carbons, which would be based off of hexane. and this then would become hexanone. Here again, we got more than 5 carbons, so a 1 and a 2 would give it the smallest number, and that is what we should end up with on that one. Any questions on that one? Same thing here. Longest carbon chain is actually just to here, not including the chlorine. Yeah, sometimes people see the C and go carbon. So it's actually just what's in the box there, which would be 1, 2, 3, and 4 carbons. So that is going to be based off of butane, which would be butanone. And really, this is carbon 1. This would be carbon 2. This would be carbon 3. This would be carbon 4. This would be 4 chloral butanone. In this particular case, because it's 4 carbons, you really don't need it. I have seen people put the number 2 there, but it really is going to be 2 no matter which way you do on this thing. So you really don't need it until you get to 5. And that would be the name there, 4 chloral butanone. Any questions on either of those there? Okay, so now that we've talked about naming aldehydes and ketones and drawing them, let us talk about some reactions that all these guys go through. I might skip ahead through some of these as we talked about really the reactions of alcohols and thiols and stuff like that last time. Obviously, all these guys could go through a combustion reaction, really like our alcohol here. Going through our combustion reaction. Let's still talk about this reaction here, which is an alcohol reaction, which we did not talk about. And this is a dehydration of an alcohol. So dehydration means that essentially you're going to remove water. It's basically what's going to happen in this reaction. So when we look at an alcohol like this, the water is removed really the same way that water is put on, and water is put on as H and OH is sort of how water is put onto a molecule, and it actually goes off the exact same way. So the easiest way to figure out what's going off is it is always going to be the OH that's going to go off. And then it's going to be a hydrogen on a neighboring carbon. It can't be the same carbon, so it's got to be on the neighboring carbon. In this case, there's only one carbon to choose from, which is the guy to the left. So you could actually change any hydrogen you want there, but that is where the water is going to come from. So these two guys is basically what the water is going to come from. Now, when we put this on, we put it on an alkene, which is a double bond, and we break the double bond to make room for it to come on. So now that we take it off, we actually are just going to put the double bond back on so that everybody has the right amount of bonds. So basically water comes off and a double bond goes on. And the double bond goes on between the two carbons, obviously, that you remove the two things from. And again, nothing else changes. So here's our H, here's our H, here's our H, here's our H, there's our carbon, there's our carbon, other H, and other H. So absolutely nothing changes except that we take that off and then slap a double bond between the two. This happens with an acid as a catalyst. That's what this means, H+, an acid catalyst. And heat, basically, right? Like you remove water by heating it, right? It goes to steam and it goes off. And that's a common thing that you need here. Again, heat is also sometimes abbreviated with a little delta symbol over the arrow. Sometimes you'll see that to represent heat. So in a dehydration reaction, you basically take water off. Now, if there's an option, for example, let's do something like, I'll do this guy here, and maybe I'll draw this hydrogens on this guy here. Draw those hydrogens out. All right. Now, in this case, we definitely would, if we were going to do our dehydration reaction here, we're going to take the OH. But now we do have a choice, right? There's a carbon to the left and there's a carbon to the right in terms of where we could take the hydrogen from. Now, the rule is when you're taking the water out in a dehydration reaction, the hydrogen gets removed from the carbon that has the least number of hydrogens to begin with. So what we're talking about is this carbon here, which has directly attached to it how many hydrogens? Just one directly attached. This carbon over here has 3 hydrogens directly attached. So in this situation, we actually would take it from the one that has the least number of hydrogens, and it would come from this one. And that is where the double bond would actually happen between those 2 carbons. And if we did that, we would end up with CH3, CH3, our double bond right there. And I will just draw CH3 without drawing the hydrogens out in that case. So if there's an option, the one with the least number of hydrogens is the carbon that should have the hydrogen removed from when you're dehydrating a alcohol to make an alkene, basically, right? We just made an alkene, which is a double bond. Obviously, water would come out as well in this case. Question on that there. Obviously, if there is no choice, you just take a hydrogen from the guy to the left there or to the right. But again, if you do have a choice, you should take it from the one with the least number of hydrogens to start with. And again, make the double bond between the carbons that lost the 2 things. Any questions on that one there? You do right here. Yeah, so the H2O will come off. And again, it's always going to then double bond between the 2 carbons where you removed basically water from. Yeah. Obviously, in the case on the bottom here, the original one, there was no option other than the guy to the left. So once again, though, we do double bond right where we remove the water from. Everything else stays the exact same, just like everything else. Nothing crazy happens other than water goes off and you throw a double bond between the 2 carbons. And again, you have pretty much the structure that is there. All right, so we're going to kind of go ahead here on these since we've talked about these guys as well. All right. We also talked about the oxidation reduction reaction of thiols last time. Let's talk a little bit about some tests that occur that can help you determine a aldehyde versus a ketone. And there's 2 types of tests. One is what's referred to as the Tollens test. And in the Tollens test, we use the Tollens reagent, which is silver with a +1 charge. Silver gets oxidized and loses electrons. I'm sorry. So it gets reduced. I'm sorry. So the silver here gets reduced and gains electrons and becomes solid silver on the right-hand side. And this occurs as the aldehyde gets oxidized. So let's revisit one alcohol reaction that we talked about, which was a secondary alcohol. I'm sorry, primary alcohol. Let me spit that out right there. We go. So we take our primary alcohol, and remember that when we throw it through an oxidation, what occurs is we do lose H2, which is the H off of here and the H off of here. And just like what we just did there, we're going to make a double bond right between the carbon and the oxygen, and that is going to give us our aldehyde group. And if you remember, we could then take this primary alcohol that's now become an aldehyde, and we could oxidize it one more time. And this oxidation, though, introduces oxygen. And again, remember, that's another definition of oxidation. And it introduces the oxygen at the end here. And this makes what is known as a carboxylic acid here. So when you take a primary alcohol and you oxidize it once, you get an aldehyde. If you take that aldehyde and put it through an oxidation, you will get a carboxylic acid. And that is different than what happens when you take a secondary alcohol. and you oxidize it, you get again, H and H come off. You get your ketone. I'm just going to straighten out the ketone here by drawing that guy to the right. You get your ketone that is made in this case. Obviously, H plus comes off. And that is the result of a secondary alcohol going through an oxidation reaction. So kind of like what we talked about, I think, last week. Now, if you go to try to oxidize this one more time, because really the carbon there doesn't have a hydrogen, is problematic there for the oxidation to occur. So you get no reaction that occurs. So nothing happens at that point. So in this particular case, we could take an aldehyde, treat it with the Tollens reagent, and the silver is going to be reduced, which means to a carboxylic acid. The process of that is the silver will then become reduced and make what is sometimes referred to as the mirror test, because it makes like silver that looks like a mirror, basically. And that would be a positive test for the presence of an aldehyde, because it was able to go through the oxidation to a carboxylic acid. If you did that with a ketone, you would not get the silver. So it'd be a negative test, because the ketone will not go through oxidation to a carboxylic acid. So you won't get that occurring. So this is a nice test that you can use to tell the difference between an aldehyde and a ketone. If you get a positive test, then it is going to be a aldehyde that you started with, and you will make a carboxylic acid. By the way, to name this carboxylic acid, that is one carbon, two carbons. That is based on ethanol. It becomes ethanoic acid. You basically take the ketone name, or the aldehyde name, and put IC at the end of it, and acid is ethanoic acid. A more common test as well that you can use to help you decide between an aldehyde and ketone is the Benedict test, which I think you guys did when you did the dialysis bag, I think, usually. That kind of orangey, pukey kind of color. Should be reddish, but not an orangey. And that is also a test that you could use to determine whether or not you have an aldehyde or a ketone. Same thing happens here. You got copper 2, which is blue. And through this process here, it will be reduced to copper 1, which will be kind of a, I don't know, orange color, I would say. Maybe a red, brick red color. I'm not sure about that. Depends. But I think in our lab, it probably looks more reddish or orangey type color. Once again, this would be the result of our aldehyde going to a carboxylic acid. And that would be a positive test for the aldehyde. Again, if you did it on a ketone, you would get no reaction. You wouldn't see it go to that orangey color and stuff like that. So for example, I think the lab you do this week, you hit it with the Benedict reagent. And if you get a positive test, that means you started with an aldehyde. You get a negative test, that means it was probably a ketone in your experiment per se. Not in every situation, but specifically for the experiment you're doing, it means it's a ketone. I think you might even have like an iodine test maybe that you could do for the ketone, I think, to verify that it is a ketone. But that is sort of the idea of the Benedict test here. Question on that there. So once again, if I had my and I threw it through an oxidation, what is going to happen is this is an aldehyde. At this point, it will be oxidized to a carboxylic acid. Once again, nothing changes except we're just going to insert an oxygen right there. So you should just copy exactly what it looks like on the other side. CH3, CH2, CH2, C double bond, and then put the O in there. And that is the only thing that changes. So aldehyde to a carboxylic acid, you basically just insert an O right there. That's absolutely the only thing that changes when you're doing that oxidation. Everything else should look exactly the same. Just put an O in place there. That gives you, again, that carboxylic acid group, which is this group here. And again, if we were to name this, this would be 1 carbon, 2 carbons, 3 carbons, 4 carbons. That is based on butane. Because it is a carboxylic acid, it becomes butanoic OIC acid. You do not need to give the location of this, much like the aldehyde. That's got to be carbon number 1. It's always got to be at the end. So the carboxylic acid group that is formed as a result of this will always be at the end, because once again, the hydrogen is there. So it's always got to be at the end. And if you did this reaction with the Benedict's reagent, you should see it turn orangey red. And again, that would be positive that you started with an aldehyde. Again, if you did the exact same guy, except that perhaps, well, almost the exact same guy, it was a ketone here, you're going to get no reaction with the Benedict's reagent. It will just probably still look bluish, I would assume. And again, that's how you know it would be a ketone in this particular case. Any questions on those reactions there? All right, we will lay it up there for today, I think.